Alright, let's go ahead and get started on our unit on chemical equilibrium. So far we've asked the question, what happens, and how fast and by what mechanism does this reaction occur by? We are able to answer both of these using stoichiometry and then kinetics. So now what we want to do is ask the question, what extent does this reaction happen? Not every reaction is going to occur to 100% efficiency. Sometimes reactions will go both forwards and backwards. So that's the next question that we want to ask ourselves. So let's go ahead and consider something in equilibrium state and figure out what that actually means. So what we want to do is we want to assume that for a given reaction that we have a complete conversion of the reactants to the products. Okay, well, what do we mean by complete conversion? Well, for each different reaction is going to have a unique amount of products that can be formed. So here, whenever we look at this first graph, this is a plot of rate versus time. And what we'll see is the forward rate of a reaction is given by red, the reverse rate is given by blue, and as time progresses, these rates start to converge upon each other until we have equal rates. So that means the forward rate is now equal to the reverse rate. And this will give us a steady state, just like we used in kinetics whenever we used a steady state approximation for fast and reversible reactions. So whenever we have the forward rate equal to the reverse rate, we can say that we've reached chemical equilibrium. So we also need to note the difference between different arrows that we'll see. So if we see a solid arrow pointing to the right, so a one-sided arrow, that means that that reaction only goes on to form products. The reverse reaction is not prevalent. If you see a double-sided arrow, which sometimes we will see as harpoons, that means that both the forward and the reverse reaction are prevalent. So here, if we look at our next plot, we show a plot of amount versus time. What we'll see is we usually assume, unless we're told otherwise, that the concentration of our products starts down here at 0. We're given an initial concentration of our reactants, which in kinetics we were given A0. What we'll see is with over time, and this is just, it doesn't necessarily have to cross paths, okay? We don't have to have this intersection. This is just an example. Is the concentration of the reactants is going to decrease and the products is going to increase. And once we've reached chemical equilibrium, so the change in the reactants and the products slows down, and eventually this change in concentration is 0. Whenever that concentration changes 0, we are said to have reached equilibrium. So let's go ahead and take a look at some data. This is for the decomposition of dinitrogen tetroxide going on to form nitrogen dioxide. So here, what I want you to look at is we are given initial concentrations for both the reactants and the products, and then we are also given equilibrium concentrations. Okay, so as we look through the experiments, we vary whether we start with only reactants or only products, and this reaction is reversible. It can go either forward or backwards because of the double-sided arrow. So, but it only reacts until it's reached equilibrium, and then we'll say that it's still reacting. The concentrations more or less remain static. So what we mean by that is we've obtained an equilibrium concentration, but it's still forming products, and products are going backwards to form reactants. So we have a static concentration. And what we'll see is no matter what the mixture is that we start with, whether we start with only reactants or only products, or maybe if we start with a little bit of both, we're able to establish an equilibrium concentration. And we find that if we take the products over the reactants and we raise it to the exponent is the coefficient, excuse me, so we have NO2 squared over N2O4. If we take those equilibrium concentrations and plug them in, we get the same equilibrium constant for every reaction, regardless of what our initial concentrations were. Okay, so even though the equilibrium concentrations are different, we can still calculate a constant from the concentrations at equilibrium by using this expression of products over reactants, and then we raise the products to the coefficients. So this is our equilibrium constant Kc. So if we look here, we have our generic reaction. A plus B goes on to form D plus E. Our equilibrium constant for this reaction, we write with a capital K, and then we use a subscript C here to denote concentration, but it's just products over reactants. So for instance, for this reaction right here, N2O4 going on to form NO2, we would write Kc equals the concentration of NO2 squared over N2O4. Okay, so whenever we're writing an equilibrium constant, there's a couple things that you need to remember. Your equilibrium constant can be gases, or they can be molecules or ions in solutions. So, if you don't see a G or an AQ in parentheses following your reactants or products, we do not include those in the overall equilibrium constant. Those are said to be unity, and we'll discuss that a little more in class, why that is, but it has to deal with their concentration. Alright, so like I said, whenever we write out an equilibrium constant, it is Kc. The C is for concentration. This is also known as the law of mass action. The law of mass action, that's just another way to say that the equilibrium expression, so the expression for Kc. Equilibrium constants at a given temperature will always have the same value. But as you change the temperature, the equilibrium constant changes as well. So equilibrium constants are temperature dependent. So if you increase the temperature, your equilibrium constant will change. And we can't say yet whether it will be greater than the original K or less than. It depends on the type of reaction and then also the enthalpy. So whether it's an endothermic or an exothermic reaction, but we'll explore that a little bit later. The good news about this unit is that this is finally a K that is reported without units. So, and the reason this is because we consider the concentrations to be ratios, and that we're dividing each ratio by the thermodynamic standard state concentration of 1 molar. So all of the units will cancel out. So equilibrium constants are dimensionless. So let's go ahead and take a look at a forward reaction here and then a reverse reaction. And this should say, instead of C plus D, I should say D plus E. And the same thing down here. Alright, so if we write Kc for the forward reaction, where we call A and B our reactants, we would have Kc is equal to the concentration of the products raised to their coefficients over the concentration of the reactants raised to their coefficients. So if we consider the reverse reaction, so with the reverse reaction, we'll start with D and E. Those now are the reactants. We would now have K prime sub C, so that prime just indicates that it's the reverse reaction. So now we have the concentration of A to the little a times B to the little b divided by D to the little d and E to the little e. So we can write an equilibrium constant whether it's a forward or a reverse reaction, and we can actually relate the reverse reaction, Kc prime and Kc. So if you notice, it's just that the numerator is swapped with the denominator from Kc prime. So we can actually write an expression. The equilibrium constant for the forward reaction is equal to 1 over the equilibrium constant for the reverse reaction. So then we would just, since we're dividing by the equilibrium constant for the reverse reaction, our reactants and products would switch, and we would end up with Kc up here. So these are all useful relationships to notice, because we might have to use these to solve for equilibrium constants for reactions that are reversed, or maybe if we change the multiple, if we change the coefficients. So let's go ahead and take a shot at writing some of these equilibrium equations for gas phase reactions. So let's go ahead and look at our first reaction. So why don't you go ahead and pause this and try to write the equilibrium expression for both of these reactions. Alright, so what we should find is that Kc for this reaction is equal to the concentration of NH3 squared over the concentration of N2 over the concentration of H2 cubed. Then if we write our equilibrium expression for the next reaction, we notice that this reaction is just the reverse of the first reaction. So we can actually write here that Kc prime is equal to 1 over Kc. So it's just going to be the inverse of that original reaction. So let's go ahead and calculate Kc and Kc prime at this given temperature where we know the following equilibrium concentrations. And usually it will state for an equilibrium problem, if it says calculate Kc, if it doesn't specify that it's an initial concentration, it means it's an equilibrium concentration. But generally, I'll try to specify that it's an equilibrium concentration. So calculating Kc, we'll plug in the concentration of NH3, so we'll have 1.6 times 10 to the negative second, and then that will be squared, divided by the concentration of N2. And remember that all of these become dimensionless because they're divided by that standard state thermodynamic value of 1 molar. So you end up with this expression. Whenever we plug and chug, we get Kc is equal to 170 without units. Watch your orders of operations. Make sure whenever you plug this into your calculator that you have your whole denominator in parentheses, or you solve for your denominator and your numerator separately and store them as variables whenever you're plugging in your calculator. Alright, well, if we know that Kc is 170, we can go ahead and solve for Kc prime, taking 1 over 170, or you can go through and plug in all these concentrations using an equilibrium expression, and you should get that Kc prime is equal to 5.9 times 10 to the negative third. And again, that is dimensionless. Alright, here's another example where we can try to write our equilibrium constants. Let's go ahead and do that really quick. So, whenever we look at these reactions, notice again that these are just reversed reactions. Okay, so from our first reaction, we'll write Kc is equal to SO3 squared over SO2 squared times O2. Okay, this reaction is the same but the opposite sign, so we can write Kc prime is equal to 1 over Kc, or in this case, if we want to actually show it, we'll have concentration of SO2 squared times the concentration of O2 over the concentration of SO3 squared. Alright, so the next thing we want to do is we want to go through and solve for this with some equilibrium values. So these are equilibrium concentrations. So you want to start to take note whether it says equilibrium, because if it says initial, then we're going to have to do something else, and we'll figure that out in a little bit. but we want to make sure that it says equilibrium. So why don't you guys go ahead and plug in and check your answer to see that you get Kc equal to 7.9 times 10 to the fourth. And Kc prime is equal to 1.3 times 10 to the negative fifth. Alrighty, so that will do it for today's lecture. Next time we meet, we'll talk about this problem whenever we start to talk about things dissociating or reactants going on to form products and how we can calculate an equilibrium constant from there. And we'll also start to explore what happens whenever we're given a pressure instead of a concentration, and how can we relate that, both the equilibrium constant with respect to the pressure and the equilibrium constant with respect to concentration, to each other, perhaps using the ideal gas law.